Facts open. We left off doing, what was it, y-intercepts, zeros. We seemed solid with it. So we're at the end of 1-2. There was really only one or two things left. They're small. It's algebraic proof. They're simple, assuming you can algebra. Sure. Reminder, if you did not turn in your chapter 0 packet, get those in. If you have your daily checks, assignments, that kind of stuff in a separate notebook or anything like that, I'd said turn it in at the end of class today, and then I will do the notebooks next hour so that you can pick it up and you're good to go. But yeah, y'all know what symmetry is. We talked about axis symmetry with parabolas. We've also seen them with absolute value. There are specific kinds of symmetry. Yeah, I might have something that is symmetrical. Like, say it's my grid, and I have a parabola off to the side. Wake up, Frank. Thank you. So this parabola, yeah, it is symmetric about its own axis of symmetry, but it's not one of our special kinds of symmetry. Special kinds of symmetry are it's symmetric to the x-axis, y-axis, or origin. The reason they're special is because you can prove them very simply. I think I told you all before, the further you go up in math, the less you're going to do math and more going to prove math. Okay, this is just a little taste of that. Please tell me you did algebraic proof in geometry, like coordinate proof, algebraic proof. You're plugging in x sub 1 and x sub 2's into formulas. You're finding distance formula with them, using them to prove, like you're supposed to derive the equation of a circle from that.
A little bit.
Some of us are saying yes, some of us are saying no. Okay. It's along that same venue where it's not tough, but if you've never done it before, y'all remember in the first stages of geometry when you had to start proving things like, prove that this angle is congruent to that angle. And you look at it and say, look at it. Why do I have to prove this? Like, I could trace it and move it over here. Is that good enough? No, you have to do the full, like you have to have the reasoning, right? That's what this is. The symmetry test, test for odd and even, definition of limits, that kind of stuff is heading into, can you actually prove it? Can you show it? Do you know the definition of it? So, if I have something symmetric to the x-axis, pretty simple, if I had a coordinate like 4, 3, then the coordinate for -3 also exists. So I can replace y with -y in the equation itself. I can parenthesis throw in a -y in place of y, and it's not going to change anything. Like the proof for those is so simple. It'd be like, say I had x is y squared minus 4. So that'd be a sideways parabola. To prove that that is symmetric to the y-axis, I throw in a -y. And then I simplify it, and hey, look at that, I end up back at the exact same spot. Like, that's the proof. You say, but, duh, look at it. You still got to show it. Okay, that's the difference between proving with a symmetry test versus looking at it and saying, believe me. Okay, so it's really, really simple. I can also do, sometimes they'll have you do it algebraically. This is just a really big minus sign. Um, Sometimes they'll have you do it algebraically. Other times they'll say, prove algebraically, support numerically. If I was to support numerically, you would take one of the coordinates, plug it in, and say, hey, look, it works. Then you would negate the y on it, plug it in, and say, hey, look, it still works. That's it. So the proof for these is not difficult. It's more tedious than anything. Same thing for if I'm across the y-axis. Say I got a point at 2, 4. Then its buddy on the other side is going to be at negative 2, 4. I negate the x to show symmetry to the y-axis. So say a standard parabola, like this one right here, could have been negative x squared plus 5. Something like that. To show that that's symmetric to the y-axis, I would plug in a negative x and then simplify it and show, hey, look, it's the same thing. Just like the very beginning of geometry, remember those very first proofs, like angle A plus angle B equals 180. You're like, but it's a line. Look at it, it's a line. You still got to show it, okay? Symmetric to the origin, both, right? Because if I reflect something over the y and then reflect that over the x, I end up like a 180. Like if you want to see how this really works, you take your paper, you flip it upside down 180, you should have the same picture. And you negate x and y. So example of that would be like your standard cubic. If I negate both, I would negate my y, I would negate my x, I would get a negative y is a negative x cubed, and when I divide both sides by a negative, oh hey look, it's the same thing. Okay? So these are called the symmetry tests. If you go further on in math, when's the next time you're going to do this kind of stuff? Probably a little bit in Calc 1. You're definitely going to do proof of trig identities in trig, where that's just a lot of substitution. It's not a big deal. But stuff like this, probably Calc 1. Definitely Calc 2, 3, and DiffyQ. You'll see those a lot. But you know, we call it pre-calculus for a reason. We're teeing that up so you can go on to the next stuff. So that's what they mean. See it in action. They say use a graph of each equation to test for symmetry with respect to those three things. Now, they would like us to literally test all three. That's a lot of writing. So what I'm going to say is if it looks symmetric to the x, just do the x. If it looks symmetric to y, just do y. Origin, just do origin. If it looks like it's symmetric to all three, okay, now you got to do all three. Sometimes you get like a circle or something, you know, something's perfect. If it looks like it's symmetric to nothing, do you remember hearing the phrase proof by contrapositive? Okay, contrapositives or proof by contradiction. You were introduced to it in geometry where if I want to say this is symmetric to nothing, I have to show all three don't work. So by showing it doesn't work to any of them, I have shown it is not symmetric. Okay? Those suck. It's just tedious. Contestant 1. I'm just showing you because I know a good chunk of you are headed up to the big leagues and you're going to be seeing this kind of proof. So this is just baby steps. It's training wheels. How do I graph that? Okay, get y by itself. We're used to doing that, right? So I'll subtract x. Divide both sides by -1. How do you get y by itself? Square root. We are putting the square root there. So y is plus or minus the square root of x minus 1. Y'all remember trying to graph this in Algebra 2? For a regular square root function, we always restricted the range, so it was just the top half, because otherwise it's not a function. This, it's not a function, because I got plus or minus on there. I can still graph it. You put the positive root of x minus 1 in y1, and then you put negative root of x minus 1 in y2. And you'll see both parts of the graph. So you got to kind of piece it together. Okay? Now, go ahead and dump that in. What does it look like it's symmetric to? So, positive part in y1, negative part in y2. What does it look like it's symmetric to? Okay, if you got no idea what a graph looks like, this is how you do it. Should be symmetric to the x-axis. X-axis is horizontal left to right. Okay. So, well, most of you just came out of Algebra 2. You remember how to graph a radical. Remember our transformations, right 1? Perfect square steps on their side. Up 1, right 1. Up 2, right 4. Up 3, right 9. Mirrored across an axis of symmetry, the negative version. So, it looks like it's symmetric to the x-axis. So I'll prove that it's symmetric to the x-axis, and I'll support it numerically. For supporting numerically, I want a coordinate that's on this graph. Sometimes there's a nice, easy integer coordinate right on there that I can use. Sometimes there's not, and I have to just throw an x in there, get the y that goes with it, and run with it, no matter how nasty it is. As long as ugly equals ugly, it's still okay. So do we see a nice integer intersection that this goes through, or a nice integer coordinate? Come on, you. Like right here, I'm at 2, 1. Or right here, I'm at 1, 2, 3, 4, 5, 2. If I'm going to support this numerically, I should be able to take x minus y squared equals 1 as my original. First, I have to prove that 5, 2 actually works. I plug in 5, 2. Yeah? Like, invalid dimensions. Your dimensions are off. You need to check that your plots are off because you may have cleared out your list and it's still trying to stat plot. You have plot 1 on, but if you go to stat edit, there's nothing there. You're asking your calculator, hey, I want you to plot nothing. And your calculator is like, bro, what? Okay. Now try. Okay, those little error messages at the bottom, they actually tell you what it is going wrong. Not just, I actually had a kid get in my quote book for this before. My calculator told me to quit. That's really discouraging. Like, it's not just telling you quit math. Read the message at the bottom, it'll tell you where to go. Okay, does this actually work? Does 1 equal 1? Okay. So I've shown that this coordinate is indeed on my graph. To show that it's symmetric to the x-axis, what do? I negate the y, right? So if 5, 2 is on my graph, 5, negative 2 should also be on my graph. So I'm going to plug in 5, negative 2. Does it work? Yay! That's it. Like that right there is called numerical support. Numerical support says I have shown that this thing, this coordinate, and its opposite pair are both on my graph. If I want to show that algebraically, I do the exact same thing, but only with x's and y's. I say if x minus y squared equals 1, then I should be able to negate my y and it still works. So I plug in a negative y. Lo and behold, it works. And just like the beginning of geometry, it's going to seem very tedious or obvious or unnecessary, but that is the proof for it. Again, training wheels. Now, technically, there'd be more setup with this. Like I'd say, suppose that a function or a relation exists such that it is bound by this equation. Suppose that blah, 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 blah. It's a whole paragraph. You remember paragraph proofs? Okay, you do the whole paragraph proof, and then down at the end, you would say, by definition of symmetry, this relation is symmetric to the x-axis. We ain't going to go all that far. You're just going to write that and call it good. Okay? So that's what a symmetry test looks like. What does this graph look like? Ruh-roh. What did we do last time? Get y by itself. In which case, maybe that looks a little more familiar. Y'all did rational functions in Algebra 2 for, well, if we've got some seniors in here, some upper class folks, handful of juniors, we're going to be at this weird crossroads where some of you might have had this in Algebra 1 and in 2. All of our sophomores, you would have probably only seen this in Algebra 2. Like, it used to be in Algebra 1, we moved it up to 2 because it kind of broke Algebra 1 kids' brains. But 4 divided by x, if you don't know how to graph that, graph it by table. What does it look like? Dump it in your calculator, what's it look like? Okay. I can do this, the 4 in there is essentially a vertical stretch, where if I take 4 divided by 1, no, get over here, thank you. 4 divided by 1, I get 4. 4 divided by 2, I get 2. 4 divided by 4, I get 1. If I did 4 divided by 10, well, it's like 2/5. It's way down here, right? What if I did the other way around? What if I did 4 divided by 2/5? 10. What if I tried to do 4 divided by 0? Thou shalt not. That's how I get my vertical asymptote. And then back it up to the other side and say 4 divided by -1, -4. 4 divided by -2 is -2. 4 divided by -4 is -1. 4 divided by 8 is a half. Okay, so I'm going to have, this is almost the parent function for the family of, they're called reciprocal functions. So it looks like this. What does it look symmetric to? Loud and proud. Origin. So if I think it's symmetric to the origin, I will prove it is symmetric to the origin by, remember, always use the original. If xy equals 4, I prove it's symmetric to the origin by negating both. I'd shove a -x in there, I'd shove a -y in there. Say, does it still work? Well, last I checked, negative by negative is positive, so yee, it works. Again, this is my algebraic proof. For numerical support, I just got to find a coordinate on there. Whenever you're doing symmetry, never use coordinates that have zeros in them, because they're on the line of symmetry. It's like, what if I ask, what does your reflection look like?
When your face is smashed against the mirror?
Like, you can't see it. Your face is smashed against the mirror. So you don't choose anything on the line of symmetry. Choose another coordinate somewhere outside. Find me a coordinate. 2, 2. So first, I got to show that coordinate actually is on my function. I'm going to plug in 2, 2. Yay, 4 equals 4. So this is actually on my graph. I have proven that. Yay. Now I prove that its evil doppelganger is also on my function. I'm going to plug in what? -2, -2. And show 4 equals 4. Yay. So again, this part is called my numerical support. They're not always going to ask for the numerical support, but I am going to go through it because, let's be honest, if we only worked in alphabet soup, some of us would get lost. But if I got a concrete number there to show it, maybe we're more likely to believe it. Okay? So, here we go. Let's start with just 5a. Make sure that we're doing it right. What does it look symmetric to? Just run that test, and it includes the algebraic proof with numerical support. If you don't have a nice coordinate, you might just have to plug something in for x, get a y that goes with it, and run with that. Y'all doing the creepy quiet thing again. Like, it's okay to talk. This ain't a test. Met with the humming of a projector fan. I don't get how the class of 8 could be louder than y'all. I mean, to be fair, the class of 8 has the Jensen twins in it. So they're fun. That's true. Boy, that would be a fun one variable stats collection. What's the average time that you go to bed?
Like 10:30.
All right. The average time you go to bed, the average time you wake up, average hours of sleep, average hours of screen time. You could all pull that off of your phone. So when I'm up at all hours of the night with Baby Bear, I think mine goes pretty bad. It's like 6, 7 hours. It's somewhere in the settings, or it'll be like under like a health and safety um, under the settings, something like that. Personal wellness. Depends on how old your phone is and what kind it is, but yeah. Now I'm hitting 7 when I'm like up for 3.5 hours in the middle of the night with a kid, just sitting there on the floor doing something to keep myself awake. Yeah. I'd say if you're a modern day teenager and you're under 4, you're probably okay. So, um, what does it look symmetric to? So, I start with y is negative x squared plus 6, and I will negate my x. Sounds like you're putting a hit out on your x. I will negate my x and hope that it works. Lo and behold, when I square something negative, it's the same critter. Okay, so that's it. That's algebraic proof. That's like the ground floor of algebraic proof. I need a coordinate that's on this graph. What do you think? 1, 5. Okay, so if y is negative x squared plus 6, theoretically, we're putting a lot of trust in Holly. We're going to put a 1 and a 5 in there and hope that it works. And I get 5 is negative 1 plus 6. 5 is 5. Yee, good job, Paul. And then, if that is symmetric to the x-axis, or y-axis, I've already proven algebraically, I'm going to go back and do the exact same thing with a number to show you that, yeah, this works. And I'll plug in what? Is it negative 5, 1, or is it 5, negative 1? What am I negating? Always negate the x if you're symmetric to the y. Negate the y if symmetric to the x. It's kind of like when I'm finding my zeros and y-intercepts, you always do the opposite to show it. So I'm going to plug in 5 and -1. -1 squared is 1. -1 plus 6, yay. So these aren't terribly difficult. But so far, the 3 examples we've had are symmetric to a thing, which is why I said start with 5a. 5b. Ruh-roh, Raggy. What is that symmetric to? Everybody. Now, that would suck to do all of it, so how about we split it up? Maybe actually talk to each other. One of you do x, one of you do y, one of you do origin. Go! Oh, you have to talk to each other now.
How could you do this?
Get with them, come over here. Or just be obstinate and do all 3 yourself. I know, you're given the alternative of work extra or talk to people. Yes, sir.
Just so confused. Use 5-1
Just any coordinate that's on there,
on the entire.
that's on the function. And you can find that by just plug in 1.
Where's 5-1 on the coordinate? Then? It goes by 2's.
Yeah.
So 1 was the x. It doesn't meet anywhere at 5-1.
Oh, no, it was 1, 5. The 5 went over here because it was the y.
Yeah, so 1.
1, 5.
But it's not on. It's off of 1, 5.
Dude, if they're going by 2's.
Oh, yeah. Got it, never mind.
There you go. But that's fair. I have seen times where their equation and their graph in that old curriculum don't even match. Like they literally put the wrong graph there. So it's fair. So first you got to find a coordinate that works. Man, if only we remembered geometry and knew the magic Pythagorean triples. Wait, aren't you in geometry this semester?
No.
Why not?
I don't have to take it.
Yeah, you do. Well, not for graduation, but if you want to go to a college, you do. You are going to hurt so much if you go to college and try to take a general.
That's my main reason. I like putting myself in pain.
All right.
Yeah.
Now, does anyone know a nice coordinate this goes through? 3, 4, 4, 3, -3, 4, -4, 3, -4, -3, -3, -4, 4, -3, 3, -4. There's 8 of them. Because, y'all remember Pythagorean triples, 3, 4, 5? No? Pythagorean triples, anything that satisfies Pythagorean theorem, a squared, b squared, c squared thing. There's 3, 4, 5. There's 5, 12, 13. There's 8, 15, 17. These are the 3 most commonly used ones, and then they're multiples. So like 6, 8, 10 is also a Pythagorean triple. Your geometry teacher tell you about the whole like cult leader thing? Like, there's a couple of you who were in here earlier. We were talking about that, right? Pythagoras was a straight up cult leader. So if I want to prove to x-axis, y-axis, origin, for x-axis I would say x squared plus negative y squared equals 25. Hey, look, x squared plus y squared is still 25. Yay. If I'm doing y squared, I would have to do negative x squared plus y squared is 25. Yay, it still works. If I was doing origin, I would negate both. Negative x, negative y. Yay, it works. Now, if you don't know those magic numbers, 3, 4, 5, I could just pick anything and roll with it. What if I just pick x as 1? What would y be? Yeah, I'll subtract 1 from 25, square root. Square root of 24, or 2 root of 6. There's a 6 in there, right? So I could use the coordinate 1, 2 root of 6, or just square root of 24, unsimplified. I can do that. I can say x squared plus, or sorry, I can show you that 1 squared plus 2 root of 6 squared equals 25. 25 equals 25. And then I can show you that 1 squared plus negative 2 root of 6 squared is still 25. That's numerical support. It doesn't have to be pretty as long as ugly works. Here it would have been the exact same thing, but I would have negated the x. Here I would have negated both. It's tedious, but I got to show you because you're probably headed up to some class where you got to prove this stuff. Okay, don't worry about the rest of it. I just want you to see it. Like, maybe one of those in the homework and call it good. Odd and even functions. Pretty simple. Odd and even are symmetric to origin and y, respectively. So it's the exact same thing. Something's an even function if it's symmetric to the y. It's odd if it's symmetric to the origin. The proof for them is over here. See how this is negative x, y. I negate the x, I should still get y. This is, I negate the x, I will get the negation of y. It's just written in function notation. Okay, so it's blah, 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 the exact same thing. You're going to be asked, is a function odd, even, or neither? And you just run that quick test on it to see if it works or not. You're either negating both or negating x. So they ask me, is this odd, even, or neither? Well, if I try negative x in there, what do I get? This is also why we need to have parentheses. Becomes a negative x cubed, a positive 2x. Compare that to the original. Aren't the signs just swapped? So if I factor out a negative, this is the negation of this, right? Negated the entire thing. So I can say f of negative x resulted in negative f of x. I go up to the top, odd or even. This is algebraic proof. It is not disgusting, it's glorious. See, this is why I wanted to show you the other ones, because you would actually plug a number in. And if I got a number that's like concrete evidence, I can see it on my graph. Algebraic proof doesn't number. You just use the variables and the function notation. And that starts to get very abstract. You understand the difference between concrete and abstract, right? Concrete is something I can get my hands on and I can work with it, I can see it. Abstract, it's like the difference between this pencil is solid. That is concrete. I can actually see, hey, look, it's solid. An abstract idea would be, this pencil is used. You're like, well, how do you define used? Well, let me get into a philosophical debate with you about that. Okay, that is the difference between concrete and abstract. All right? This starts to get pretty abstract because by the end of it, it's just alphabet soup. And you have to understand that this means the negative x resulted in negative y. This guy. I'm going to negate the x and see what happens. H of a negative x. I negate this guy. I negate that guy. I negate that guy. I'll simplify those. Getting a negative x cubed. Getting a, this guy's positive, so it stays negative 0.5 x squared. Negative negative makes this plus 3x. Compare that to the original. Is it the exact same thing? So that means it's not even. All right, see if I can factor out that negative and it ends up odd. H of negative x is, take out my negative, I get x cubed plus 0.5 x squared minus 3x. Compare that to the original. Not quite. So then at the end, I've got h of negative x does not equal h of x. That was this part. It wasn't the exact same. And it does not equal negative h of x. I plugged in a negative x, and neither of those two special things happened. So I'd say neither. Now, for those of us who are looking at this and saying, ow, like there's literally a spot on the left side of my brain that hurts right now. Try putting this in your calculator and physically look at the graph. Put x cubed minus 2x in and see what it looks like. We said that this was an odd function and we had the proof for it. If it's an odd function, it's symmetric to the origin. Take that calculator, flip it upside down. Isn't it the exact same picture?
Yep.
That's how I know it's an odd function. What I wrote up there is the proof that it's odd. And you're all going to start seeing this more and more. You are all young adults. It's not what you know, it's what you can prove. Okay? This one, plug that in, look at the screen. Okay, plug C in there, look at the screen. What do we think? Is it symmetric to the y-axis? Butterfly? Is it symmetric to the origin? I can flip it upside down and it's the same? Or is it just a little bit off and it don't work? Okay, so I should get neither as my answer. This is just the proof for neither. So now B, plug it into your calculator to start with. Put it in your calculator to start with. Look at it and say, by the time I'm done doing the proof business, I should prove that it's what? If it's symmetric to the y-axis, it's an even function. Go back and look at the top. If it's an even function, what do I do? Plug in a negative x and what happens? I get the exact same thing, the regular f of x, back out. Okay, so I'll try it. I'm going to plug in negative x. When I do, I get x to the fourth plus 2, which is the exact same thing that I started with, so I can say g of negative x is g of x. I plugged in a negative x and got the exact same thing out. This is even. You say why I kind of made a big deal the other day about f of x, g of x are not just fancy y's. Like this is the name of the function and the guts inside the function. Okay, we shorthand it in the lower classes because I want you to think about some of your, maybe some of your buddies, maybe a sibling who's a freshman, 8th grader, and think if they can understand an abstract concept like that. Y'all, I had a freshman kill my microwave that lasted 20 years because he didn't understand popcorn. Okay? It sat outside on my deck for a week. We tried to deodorize it 3 times, and the first thing that was cooked in it smelled like rancid ash. Like it's in the lining of the microwave. Like I've had that thing since my sophomore year of college. He killed it. Yeah, this one's new, but
Not the first time it happened either.
I was able to clean it after Owen did it, but it couldn't survive Dakota. So those 3, odd, even, neither. Start by looking at the graph though, because if you look at the graph, you know what the answer is supposed to be. Okay. All this stuff about functions, like, it's expected that you just know this because you took Algebra 1. But I'd say this is pretty abstract material and should not be in Algebra 1. Algebra 2, yeah. In fact, I got to look at the college algebra textbook the other day. And y'all, that's just Algebra 2 again. It's not even Algebra 2.2 like I've been saying. It's just Algebra 2 again, but for college credit. Like they don't do conics in there. They don't do nothing. If you got any friends who are doing the dual credit college algebra though, What they're finding out, yeah, it's algebra 2 again, but it's twice as fast. Want you to think your everyday algebra 2, do that every other day. Still one semester. That's why it's college credit. Not the complexity, just how fast you got to go. Okay, first one. It should look like that. Remember drawing the lame birds in the background of every outdoors picture you made in elementary school? The little checkmark birds. Okay, should look like that. Looks symmetric to the y-axis. I should come up with it's an even function. 6b, well, it's just square root. Starts at 0, heads off to the wild blue yonder. Should be neither. 6c, I honestly don't know. Because as a quintic, that thing could do all kinds of stuff. It could be in transformation form, just expanded out, so it would look like a really skinny cubic. It could have a couple of imaginary zeros, but still be symmetric. Or it could be God knows what, like this. Which is it? So it's like a condensed version of this? Okay. Does it look symmetric to anything? Symmetric to the y? Origin. X. Which is it? Okay, I heard all three. All right. The process is still the same for all of them. It's just looking at the graph tells me what my answer should be when I'm done. I should be able to plug in negative x, get 2 over negative x quantity squared. So f of negative x is 2 over x squared. Hey, look, it's the same thing. So I'm just going to keep going in a chain here and call that f of x. I have shown that the function of negative x gets me function of x. They're the same thing. Hi.
How does the graph look like that for A?
Oh, that's when it's square root, not square. Okay, sorry. That's when it's square root, not squared. Oops, it's the butt crack one, right? It like pressed ham. It looks like someone. You ever have someone in middle school do that? Like moon someone behind the bus, get kicked off the bus for 2 weeks. Then your mom was really mad because they had to bring you to school every day. There's always that kid, right? Yeah. Who would do that? But I have shown I plug in negative x, I get the exact same thing. This is even. Because this equaled that. If I plug in g of negative x is 4 root of negative x. Ruh-roh, Raggy. Hi.
So, okay, so it's even if it's not from
Absolutely nothing. Odd, even, or neither. X just gets left out of there. Yep. X isn't special enough. Well, because if it's symmetric to the x-axis, then it's not a function because it won't pass a vertical line test. If I put in a negative x, well, I'm just kind of screwed, ain't I? Because now I wasn't allowed to have negative numbers anyway. By definition, this had to be x is greater than or equal to 0. So if I plug in a negative x, this just broke math law. So that's definitely a neither. Now I would say g of negative x equals empty set. Like it does not exist. I can't do it. And that one, you said it looked symmetric to the origin? Yeah. So let's give it a whirl. I'd say h of negative x is negative x to the 5th minus 2 negative x to the 3rd plus negative x. Okay, everything's going to switch. So negative x to the 5th plus 2x to the 3rd minus x. And if everything switches, pink, yeah. That means h of negative x was negative this guy. X to the 5th minus 2x to the 3rd plus x. So h of negative x made negative h of x. That's odd. Okay. Yeah, this one I don't like that they had it's called an implicit domain. X had to have been greater than or equal to 0. Otherwise, it would have broken math law, right? Can't take even root of a negative. So it's an implicit domain, meaning they're not going to say it, but it would have certainly helped if they had this right next to it. Then it would make a lot more sense that when I negate it, it just don't work. Because now I'm taking the square root of a negative. Limits. Okay. Limits. And then we used to be able to make a bunch of Mean Girls references here, but now that movie's so outdated that people might not know them. So, Lindsay Lohan, the lush of Disney. So, a limit. A limit is as x approaches number, what is y approaching? That's a limit. As x approaches thing, where is y going? It might not equal this exact value, but y is headed there. Think of like a speed limit. You don't have to be exactly that number, right? It's just, okay, I live outside of Bell. I'm a teacher. I can't afford Spearfish. So every day I come in on 85. I get over that overpass. As soon as you hit the overpass, it goes down to 45. Don't lie, everyone there is doing 50, 55. But as soon as you get over that overpass and you look down on Spearfish Creek and the road nicely winding next to the interstate, and I see a vehicle parked in the median, I don't have to be going exactly 45, but I better be approaching it. I better be getting real close to it, right? A limit is as I get really, 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 really close to this x, what is my y doing? As I get really, really close to that cop, what is my speed? Okay? It better be approaching 45 or less. Here's how we write it. I say the limit of my function as x approaches some number. Okay, they like to say c. And then I'll have some number here. But what we like to do, this is how they write it. I would much rather say instead of c, I'd rather say as x approaches this x value, my y's are approaching this. Okay? As x goes here, what are y's doing? That's a limit. So, you approach it from both sides. If I asked what is the limit of my function as x approaches -4, I'm going to go closer and closer to -4, closer and closer to -4 from both sides of the graph. So as I come in at -4, where is my y going? There. Okay, as I come at it from both sides, it's approaching 4. Now I know that the point -4 doesn't exist. There's a hole there. But it doesn't matter. I'm approaching that value. I'm getting close to that value. So the limit is 4. I might not ever go exactly 25 through downtown. I'm just going to get really close to it. Okay? If I ask for what is the limit? No. Get back here, Green. The limit of my function as x approaches 0. What do you think? So come at 0 from both sides. What is y doing? Looks about -7, right? So that's what you write. The limit as I approach it is -7. This is why we want you to be good with your calculators. A lot of textbooks will want you to physically write out the table. Like if I'm getting really, really close to -4, they want you to show at -6 and -2, -5 and -3, -4.5, -3.5, -4.1, -3.9, -4.001, -3.00. They want you to show all of that on a table. We're going to say, nah, dude, I'm looking at my table on my calculator. You remember how to switch your table over to ask. So you ask the x value. That's how you find a limit. If I want to know what the limit of this function is as I'm getting close to 0, I'm going to put in a positive 0.00001. I'm going to put in a negative 0.00001. And as long as those two numbers are the same or very close to the same, the limit exists. I'm going to the same value. Now, this is where we said Mean Girls reference. If I said the limit of my function as x approaches -9, I want you to come at -9 from both sides. There's nothing there. The function does not exist on either side of -9. So I say the limit does not exist. Okay. The limit does not exist. In some cases, depending on what the domain is, I might be able to approach something from only one side. Like, I could do the limit of this function as x approaches -8. Can I come at -8 from both sides? No. I can only come at it from one side because -8 is where the domain begins. So what we do is say -8, and then I'm going to put a little positive up here to say I'm approaching it from the positive side. I'm approaching it from the right side. And in that case, if I come at -8 from the right side, I can still say it gets real close to what? -10, watch scale. But I have to put that little plus on there to say I'm approaching it from the right side. Like it's kind of like a disclaimer of saying, well, you need this % on your test to get B in the class, assuming that you turned in all of your daily work, right? It's that little disclaimer that goes with it. I'm saying I can only approach it from the right side. So that's all the limit is. The definition is written here, and I know it looks pretty funky. That's why I'd rather just talk it out, okay? If you just came out of Algebra 2, this part should sound familiar. If you did Algebra 2 many moons ago, maybe not. Have you heard of continuity before?
Yes.
Whether a function is continuous or discontinuous.
Yes, a little.
Okay. What if I said I can draw a continuous graph? What does that mean? How can I draw? Like, how can I physically draw a continuous graph? I never pick up my pen, right? Like, I keep going. And then if it's going to keep going off into infinity and beyond, then I put an arrow at the end. If something is discontinuous, I have to pick up my pencil to go somewhere else. Maybe there's a dot because it only exists here. Maybe there's a hole and I keep going. Maybe there's an asymptote, but I have to actually pick the pen up because there's a part of the domain that doesn't exist. The three types of discontinuity that we see are infinite, jump, and removable. Infinite discontinuity. Think about this if I'm looking at the limit of this function as x approaches c. Well, approach it from the left side. Where are the y's going? All the way down to -infinity. Approach it from the right side. All the way up to +infinity. That right there should tell you that it's infinitely discontinuous. Because as I approach this value, my graph is headed off to infinity. The limit does not exist because they're not going to the same place. They have to go to the same spot to have a limit. Okay, that'd be like if I'm coming at a particular speed trap from this side and the speed limit says 25 here, but if I come at it from this side, the speed limit says 35 back here. So, I'm sorry, ambiguous legal zone. Why is it 25 or 35 in between there? Is it 25 if I'm going this way, but 35 if I'm going that way? All right, Mr. Cop, which way were you pointed? Like, it gets a weird zone, right? They're not headed to the same place. Specifically, they're headed to infinity. So I know it's infinitely discontinuity. I would put next to this is asymptotes. Jump discontinuity. We just saw this. What kind of graphs make this? Piecewise. Okay. Now, a piecewise function doesn't have to have jump discontinuity. Because what happens if this graph, what happens if it ends exactly where the next one begins? Can I still make the graph without picking up my pencil? Mm-hmm. Yeah, I could. So just because it's piecewise doesn't mean it has to be discontinuous. But the only way that you get jump discontinuity is with a piecewise function, because you're going to jump from one rule to the next. Removable discontinuity. I think we talked about this a couple days ago. That feature is a hole. How do I make a hole? Well, that's how I physically draw it. How do I make it with a function? I have a canceled factor. Okay, so say I'd have f of x is, and then be like x minus c, x plus b over x minus c. And then I would literally remove the factor. I remove the factor, so it's removable discontinuity. A removed or canceled factor. And it makes a hole. And as we learned in Algebra 2, our calculator will not show us the hole because there's only so many pixels that it has. It's trying to show the point 2.99999 and the point 3.0001. It's, y'all know that ain't a high def screen, okay? That's like, especially the plus silvers, like that's the same kind of screen that was on my Game Boy Pocket in 1995. Okay, like that is not nice tech right there. So it's not going to show you the hole. We have gotten it to display on the screen once before, and we had to make our window down to like, the window was ridiculous. It was like less than a 10,000th of a unit. And there was just the tiniest like 1 pixel break in the line. So you got to know that the calculator is never showing you this. You have to get it from the function itself. So those are our types of discontinuity. You say, well, why did we do all this limit stuff and then talk about this? Look below that. Just like with the symmetry test, there is a continuity test. For a function to be continuous, it has to meet 3 criteria. Rule number 1. I got to plug in a number and it works. It doesn't break math law. It actually exists. Rule 2. The limit has to exist at that point. And rule 3, those 2 things I just found, they better be the same. So, go over here, example. That's not that graph. They screwed up. Oh, that's -4 over x. Where did I pull that from? Oh. So sometimes they're gonna ask, is it continuous at this point? That's how we're gonna start these problems. Later on, after we get a little practice with it for a day or so, I'm gonna just start saying, state the continuity. So if there's any points of discontinuity, you gotta find them. So they're gonna say, is f of x continuous at part A? I'm going to say, is it continuous at -1? Part B, is it continuous at 4? Part C, is it continuous at 0? So the continuity test says, 1, I got to be able to plug this number in and it doesn't break math. Can I plug in -1 and it doesn't break math? What do I get when I plug in -1? 4. Yay, it exists. I have passed the first part of my test. Next, limit. So as I get really close to -1, what is it doing? That's where we want our calculator and our table. Okay. In my calculator, I'm going to put, clear, -4 over x. I graphify, make sure that I have the same graph. Okay. So it is the same graph, we're good. They're saying as I get really, really close to -1, what is it doing? Now you could trace and then just look on either side of -1 and check out your y values and hope it's the same. Or what I'd recommend is go to your table, switch this over to ask, and you want to come at -1 from both sides. So if I said -2, -1.5, whoa, -1.9. Oh wait, no, other way around. Sorry, -1.1. -1.001. See, I'm getting closer and closer and closer and closer. 4,000 over 1,001. What's that? Almost 4. What if I was on the other side? What if I was at -0.999? -0.9. -0.5. 0. Ooh. That's interesting. Okay, fine. Negative 0.1. All right. Okay, I can see as I come at it from both sides. Now maybe it's a little harder with the fractions on there. If you want, go into mode. You can switch your fraction answers to auto or decimal. Auto means I typed it as a fraction, it'll write it as a fraction. Or just to prove to you that they're the same thing, I'll write the next one as a division problem, -4 divided by x. Okay? So it's easier to compare if they're in decimal town, right? And you see as I get really close to that -1, my numbers are getting closer and closer and closer to 4. So I just say, yeah, cool, my limit's 4. Third part of the test. Do these two things equal each other? the limit value and the function value have to be the same. Yee. So since it passed all three parts of the test, I would say it is continuous at x equals -1. Now, if I just look at the graph, this is not a continuous graph, is it? If I do, oh, I lost my green. If I plug in 4, see if we can do that a little faster. Plug in 4, does it work? Like, does it break math law or is it okay? We good. I plug in a 4, I get -1. Yay, passes. Limit of my function as x approaches 4. This is why I wanted it in my calculator. I don't need to come at it from both sides with a crap ton of numbers like that. Yo, I can just get really, really close to 4 on both sides. Put in 3.99999. Remember, the box is only so big. Arrow over and you can see it. What if I go to 4.01? Okay, so remember the column is only so big, but if I look at them, aren't they both just a hair on either side of -1? All right, I guess my limit's -1 because it's getting really close to that. Passes the second part of the test. Third part of the test, does the function value equal the limit? Does -1 equal -1? Oui. So I would say it is continuous at x equals -1. But what's going to happen when I plug in 0? The function of 0. Fail town, right? You can't do that. Oh, it was 4. Sorry, I was looking at the y part of the coordinate. Crap. Got him. I've been up since 3:05. Limit. As x approaches 0. All right. So I'm going to get really, really close to 0. So on one side, I'm going to go to -0.00001. On the other side, I'm going to do a positive 0.00001. Are those headed to the same place? One's going up to positive infinity, the other's going to negative infinity. Those are not the same spot. So I'd say the limit does not exist. And ironically enough, ugly equals ugly. But since that's not an actual number that you can prove, it still fails. Like I can't actually put in undefined into a calculator. So for that one, I would say it is not continuous. Right above that, you got to tell me what kind. Which type of discontinuity was this? At 0. Infinite, right? Because it hit an asymptote and it went to infinity, plus or minus. So I would say there's infinite discontinuity at x is 0. Okay, that is my continuity test. The solutions for this involve you writing down a whole bunch of tables, and I think that's overkill. If they ask, is it continuous at 0? This is all I need to see. You showed me the function value, you showed me the limit, you showed me the comparison between the two, and you wrote your answer. Good enough. Come on. Don't test me, Frank. I'm gonna stop there. That's a good place to start on Monday. Because I know we're not going to remember the continuity test by Monday.